Welcome to my Real Analysis Exam 3 Review Problems and Solutions video. In this video, I'm going to go through a bunch of definitions, theorem statements, true-false questions, calculations, and proofs about Riemann integration, numerical series, and series of functions. We start with some definitions. Given a series of numbers, a numerical series, the sum k goes from 1 to infinity of a sub k, define what it means for the series to converge. By first defining a related sequence. I added some extra instructions there. I didn't have to. You should know that it is related to a related sequence. What is that related sequence? It's called the sequence of partial sums. And it's through this sequence and whether it converges or not that we give meaning to the infinite series, the infinite quote-unquote sum. You should realize that when we call this an infinite sum, we're not literally saying we're adding up infinitely many things, but we can still rigorously define what it means to, and I'm not joking, pretend that we're adding up infinitely many things, and that turns out to still have applications, even though it's really a pretend adding. Anyway, what is this sequence of partial sums? For any given positive integer n, I let s sub n be the finite sum of the AKs as k goes from the lowest index, in this case 1, sometimes it's 0, up through n. In other words, this is, in this case, the sum of the first n terms. If the index started at 0 instead of 1, it would be the sum of the first n plus 1 terms. We say, once we've done this, and that makes sense because it's a finite sum, that the infinite series, k goes from 1 to infinity of a sub k, converges by definition if the sequence of partial sums converges. You can write your sequence like that. That's how the textbook that I use writes it. You could also write it maybe with this notation. Either notation's fine. This is probably a better notation, though this is how my textbook writes it. If this sequence converges, i.e. the limit as n goes to infinity of s sub n exists. You can talk about what that means in terms of an epsilon n argument in this case. I've done that in previous videos. Here we'll just say that this limit definitely does exist. Number 2, define what it means for a series like this, same kind of series in fact, to converge absolutely. Okay? I'm going to give the definition of what this means based on something that you really should remember. Then we want to make sort of a subtle comment about it and relate that to a certain theorem, even though it's not asked for here. We say a series, a numerical series like this, converges absolutely. This converges absolutely. I won't bother writing it out. If what? If this series, a corresponding series where I take the absolute values of the AKs and add those up. In other words, I do this. If that converges, the corresponding series of the absolute values of the AKs converges. If that's true, we say this original series converges absolutely. Okay, here's the subtle point. According to this definition, it's not absolutely clear that this converging means this will converge. But in fact, that is true. It's a theorem. It's not asked for here, but I'll add it as a theorem. If the original series converges absolutely, meaning, again, by definition, that means this series converges, then, in fact, the original series also converges. Okay, so it's kind of funny that way. The definition of absolute convergence does not seemingly, on the face of it, necessarily imply that the original series converges. But there's a theorem that you can prove that says it does. I'm not going to prove that theorem in this video, but I would encourage you to do so. It's not too hard. I would encourage you to try to do it based on the definition of what it means for a series to converge. Next problem, let's add some more colors here. Now we're talking about a sequence of, not numbers, but functions, sequence of functions, fn, and a function f defined on an interval I. I'm assuming all these functions are defined on this interval I. Define, once again, what it means for this sequence to converge pointwise to f on I. Okay? What does it mean for a sequence of functions to converge pointwise to some other function on a given interval? Notice here that I did not put any x's anywhere. Okay? In the setting where you're talking about pointwise convergence, and in the next problem, uniform convergence of sequences of functions, and then also talking about the corresponding pointwise convergence and uniform convergence for series of functions, it's good to emphasize the distinction between a function like f and its output, f of x. Okay? F is a function, f of x is the output of f, which really means in this context it's a number. So you really want to make that kind of subtle distinction emphasized here. All right, let's get into the details. This is a fairly easy, simple thing. It's going to converge pointwise to f on I. Again, I'll just pretend I've written that there to save some time. If what? If, it's pretty simple actually, the limit as n goes to infinity of f sub n of x, now I do put the x in here because these are going to be numbers, if that equals f of x, not just at one value of x or two values of x, but for all x in the interval. I'll do an upside down a for my universal quantifier for all x that are elements of the interval I. Okay, and it's that fact that, along with this, is the part of the definition of pointwise convergence. It doesn't mean that this convergence occurs at the same rate, you might say, for all x. How quickly fn of x converges to f of x could vary quite widely in theory, depending on what value of x in the interval that you're at. The next problem makes that kind of idea, you might say, makes that kind of idea a little bit more precise in the context of when we would like the convergence rate to be approximately the same. That's a little confusing. Let's go ahead and make this definition here. Given a sequence of functions again, fn and a function f, all defined in an interval I, now define what it means for the sequence of functions to converge uniformly to f on I. Not pointwise, but uniformly. Intuitively, this means they converge, no matter what x is, it converges at about the same rate. Now that's kind of a vague statement. We need to make it precise. Okay? And this definition, if you're going to define it correctly, does require an epsilon n kind of description. Sometimes you have epsilon delta descriptions of definitions of convergence. Here we have epsilon and n, where n is some positive integer. This is going to happen if what? If for all epsilon greater than 0, you see a lot of definitions in a real analysis start this way. Epsilon is my measure of closeness that I would like to attain, so to speak. It's my target. If for all epsilon greater than 0, there exists a sufficiently large capital N. For all epsilon, no matter how small, there's a sufficiently large capital N. Now, you don't have to put the words no matter how small for epsilon and sufficiently large capital N in the definition. That's kind of what you're thinking intuitively, though. No matter how small the epsilon is, there's a large enough value of n where the fn of x are going to be close to f of x. And here's where the uniformity comes into play for all x in the entire interval. For all epsilon greater than 0, there exists a capital N in the natural numbers such that the distance between fn of x and f of x, denoted by the absolute value of their difference, is small, is less than epsilon, as long as the little n is greater than or equal to capital N. In other words, the little n is sufficiently large, and for all x in the interval. And that extra part there is absolutely necessary for the uniform convergence. Hopefully your teacher has taught you a way to visualize this. The intuitive idea here is you got some function f, and there's its graph. And well, let's go ahead and call this graph y equals f of x. I'm graphing that in an xy plane here. And I could also graph two other functions, a vertical shift of this function upward by epsilon units. That's the original graph. Here's the graph of y equals f of x plus epsilon. Down here's the graph of f of x minus epsilon. And to say that the sequence fn converges uniformly to f on I, and down here's the interval I, means that no matter how small this epsilon is, no matter how skinny this tube is, there's a large enough capital N so that if little n is greater than or equal to capital N, all the fn of x's functions have graphs that are stuck inside the tube between these two outer functions for all x in the entire interval, as long as n is sufficiently large. Okay? And that can be done no matter how skinny that tube is. Though the skinnier it is, the smaller epsilon is, the bigger capital N needs to be. Number 5 says, state the ratio test in its strongest form with the idea of limsup and liminf. Okay, so maybe you've seen this in your class, or in your real analysis class, maybe you haven't. You've seen the more simple version, weaker version, in calculus classes before that just involve ordinary limits instead of limsups and liminfs. Talk a little bit about limsups and liminfs as I talk about the ratio test here, but I'm not going to go into a ton of depth. Here's the setup. Suppose you've got a series. The ratio test is about confirming that a series converges or diverges, or perhaps the ratio test gives you no information. That does happen sometimes as well. Suppose you've got a series of non-zero terms. So all those a's are non-zero. Of course, if any one of them were 0, you really could get rid of it, so to speak, and create a new series that had all non-zero terms. It's important because we're going to be needing to do some divisions, and we don't want to divide by 0. There's two parts to the test here. The first part is a condition for when the series will converge, and not only just converge, but also converge absolutely, in fact. If you recall from Calc 2, you compute the limit as n goes to infinity of a sub n plus 1, or the absolute value of a sub n plus 1 divided by the absolute value of a sub n. And if it's less than 1, the series converges. In fact, it converges absolutely. That's still true, but that's the weaker form of the ratio test. The stronger form involves a limsup here. Instead of LIM, we write LIMSUP of the same kind of ratio. Go ahead and put absolute value signs around the whole thing. Another notation for the limsup is to write a limit sign with a line above it like that. That's also notation for the limsup. If that's less than 1, then the series not only converges, but converges absolutely, which, again, also mean it converges. Why do we write this, and what does it mean, and why is it stronger? I can't really fully explain that in a real short amount of time. Here's the basic idea, okay? A limsup and a liminf oftentimes will exist as real numbers, and not necessarily plus or minus infinity. I'm talking about real numbers here, even when the limit of a sequence does not exist. For example, here's the simplest case I can think of. Consider the sequence that bounces back and forth between 1 and -1. That's a sequence 1, -1, 1, -1, 1, -1, 1, -1, whose limit does not exist. But it does have a limsup, a limit superior, and a liminf, a limit inferior. There's a real technical definition, but basically the idea is the limsup is the number that is the highest possible limit of a subsequence of the given sequence, and the liminf is the nth, the lowest possible real number. Did I say that right? Yeah, the lowest possible real number, that's the limit of some subsequence. If you got your sequence bouncing back and forth, 1, -1, 1, -1, an example of a subsequence is, well, 1, 1, 1, 1, 1, 1, take every odd term in the original sequence, and that sequence converges to 1. In other words, positive 1 is a possible subsequential limit. The sequence -1, -1, -1, -1 is also a subsequence, and it converges to -1. In other words, -1 is another possible subsequential limit. And in fact, those are the only two ones for for that sequence. The limsup is positive 1, the liminf is -1. So what I'm trying to say is limsups and liminfs often exist even when ordinary limits do not exist. And that's what makes this stronger. It applies to more situations. I think I don't want to go into any detail beyond that, other than to say one more thing, that if the limit truly does exist, it will equal the limsup and also the liminf, and they will be equal to each other. Second condition is if the liminf of the same kind of ratio, also written with a line below the limit sign, these are just alternative notations, if that is bigger than 1, then the infinite series, in fact, diverges. In many calculus books, you'll see a third condition that says, assuming the limit exists, if the limit equals 1, then the test gives no information. But that's not really necessary to write in a theorem, right? That's not something you would typically write in a theorem. So we can just leave the theorem, the ratio test, as just these two things, though it's good to know that if the limit exists and equals 1, the test doesn't tell you anything. The series might converge, it might diverge. There are examples where it converges, there are examples where it diverges. All right, on to the second page. Number 6, fully state the Fundamental Theorem of Calculus, both parts. In calculus books, you often see them called Part 1 and Part 2, and I could call them that here. We are going to state this. It is in a bit more general form than you typically see in a calculus textbook. Sorry, that's blurry there. Hopefully that'll get fixed here. There we go. We're going to suppose we've got a function, little f, that's real valued and defined on a closed and bounded interval. We're not going to assume it's continuous like you often do in calculus books. We're just going to assume it's Riemann integrable. In other words, the Riemann integral makes sense, it exists. We actually will do a well, we've got a couple true-false questions related to Riemann integrability, and the very last problem is going to be a proof related to Riemann integrability. I'm not going to define it here. I will talk about the definition in the very last problem. Suppose this is Riemann integrable on the closed interval from a to b. Okay, that's the initial sentence. We're not assuming it's continuous at the start. We will assume it's continuous, well, at some points at least later on here. Let capital F be a function who, with the same domain, be defined by the equation capital F of x. So capital F's the function, capital F of x is going to be the output of the function. At the input x, it's going to be a number for any fixed x. It's going to be defined as the integral of little f from a to x. Okay. Now in calculus classes, you will typically write like f of t dt here. And that's an important thing to do in calculus classes because you emphasize applications. And when you are thinking about applications, those variables are definitely good to emphasize. But when you're doing real analysis, you're not really typically thinking about applications. And so we don't need to specify what the variable for little f is. We're just saying we're integrating it from a to x. So we typically don't bother with the f of t dt, say. The variable is in the upper limit of the integral here. A is fixed. It's the left endpoint of the interval. Actually, I could pick a lower limit of integration to be any number in this interval. That turns out to be okay. Okay, what is this doing? If you have learned about this from calculus, hopefully you remember this capital F is going to be an antiderivative, or an antiderivative if you prefer, of little f as long as little f is continuous. And that is part of what I'm going to say here, but not right away. We can first say, then little f, capital F is continuous on the closed interval from a to b. That's the first thing that we can say. And that's true even if little f is not continuous, as long as it's Riemann integrable, which is related to the fact that there are certainly some discontinuous functions that are Riemann integrable, which is related to this question down here, peeking ahead. Also, capital F is differentiable, has a derivative at each value of x in the interval where little f is continuous. That's continuity at a point. Even if it's just continuous at one point in the interval, the capital F would be differentiable at that one point. Sounds a little strange. Can that really happen, you might wonder? Okay, let's not worry about it. And capital F prime of x, the derivative of capital F at that value of x, equals little f of x at all such points. That effectively is, when I said both parts here, that's effectively the first part. I mean, you could say this is part of the first part as well. Maybe I will. The second part is, so that's taking the derivative of the integral and saying you get back the function you're integrating, the integrand. If little f is continuous everywhere, then capital F will be differentiable everywhere, and this derivative will be true no matter what x is. That's how you typically think of it in a calculus course. And secondly, if capital G, say, is an antiderivative or antiderivative if you prefer, of little f on the interval from a to b. In other words, g prime of x always equals little f of x for all x in the interval. I won't bother writing that, but that's what that means. That would be in a situation where little f is continuous, though I'm not assuming that here. Then the integral of little f from a to b can be evaluated by doing capital G of b minus capital G of a. And since in part 1, the second sentence, if little f is continuous everywhere, then capital F is differentiable everywhere and its derivative is little f. Capital F would be an antiderivative of little f over the entire interval in that case, and I could use a capital F instead of a capital G down here. But it's really two separate statements here. Okay? Should have given myself more room there. All right, number 7, state the Weierstrass M-Test. The Weierstrass M-Test is about convergence, in fact, uniform convergence of series, not of numbers, but of functions. It's a condition, a sufficient condition for uniform convergence of such a series. And series of functions can be related to sequences of partial sums, sequences of functions that are partial sums of the series of functions. What does the Weierstrass M-Test say? And we're going to make use of the Weierstrass M-Test later on for some proofs here, or some calculations at least. It says, suppose you've got a sequence of functions, call them fk or fn or whatever you want. I'm ultimately going to be adding these functions, but initially it's a sequence. It's not the sequence of partial sums because I'm going to be adding them. There would be a related sequence of partial sums. Suppose fk and f well, let's see. We actually don't need an f here. We don't need to specify what the sequence or the series of these functions is converging to. Suppose you've got a sequence of functions. Defined is a sequence of functions defined on an interval I. Also suppose that there exist numbers mk, real numbers that will be positive. I'll go ahead and say they're positive here, but it would be implied that they're positive later on. There exist mk such that, st means such that, the absolute value of f sub k of x is less than or equal to m sub k for all x in the interval. Then, if the series formed by adding the mk's converges, the conclusion is then the series of the fk's converges uniformly, and I should say what the interval is, on the interval I. Uniform convergence is always with respect to some intervals. So you might have a sequence or a series of functions that converges uniformly on some interval, but not on some bigger interval, even though it might be defined and might even converge on the bigger interval. So you should always specify the interval, right? That's the Weierstrass M-Test, a sufficient condition for when your series of functions is going to converge uniformly on the interval I. It's a handy thing, and again, we'll make use of it. True or false? If f is continuous on the closed interval from a to b, then it's Riemann integrable on the interval from a to b. That's definitely true. Though, of course, it takes proof when you do theory of Riemann integration. We're not going to do a heavy-duty proof related to Riemann integrability here, but we will do a relatively easier proof. Though it's not easy, at the very end, that'll be our last problem again. Number 9, if f is Riemann integrable on the closed interval, then it's continuous. That's a false one. Like I mentioned, hinted at up here, there are discontinuous functions that are Riemann integrable. In fact, the very last problem is going to be a step function with a step discontinuity that is going to be Riemann integrable. So that is false. Number 10, the series that you see here converges absolutely. Is that true or false? Well, you'd have to consider the corresponding series of the absolute values of these things. I can get rid of that negative 1 to the k plus 1, and I can also get rid of the absolute value sign after I do so. And you should recognize, based on things you've learned in the past, even in calculus, that that's the harmonic series, and everybody should know, all math majors should know at least, the harmonic series diverges. And that means this is false. It does not converge absolutely. Though, I could have had another question, but I didn't here. This series actually does converge. This one doesn't. This one diverges, but this one converges. It's called the alternating harmonic series, and it converges by something called the alternating series test, which is not going to be a subject of this test, this exam here. But it does converge, just not absolutely, because that diverges. Okay, and non-absolute convergence, sometimes called conditional convergence, is sort of like a weaker kind of convergence. It's not as well behaved, you might say, in some ways I won't specify. Next one, if a sequence converges to 0, then the series converges. False. Why? There's an example. The 1 over k's, the terms of the harmonic series converge to 0, but the harmonic series itself diverges. So just because this is true doesn't mean that's true. However, if you flip it around, the converse statement, if the series converges, then the sequence of terms, not partial sums, but the terms, converges to 0, that is true. And its contrapositive would be true as well. If your terms do not converge to 0, then the series would diverge. Okay? That, in fact, is sometimes called the divergence test. True or false? Sum of, as k goes from 0 to infinity of 1 over k factorial is pi. That's false. It doesn't equal pi. It equals e. That's just something to know. So if that were an e there, then it would be true. Number 14, practice with geometric series, really useful and fun series. To figure out the numerical value of this sum, this series, you need to know some things. You need to know, well, first that it converges, and secondly, a formula for the convergence of a geometric series for what it converges to when it does converge. The general formula is that the sum k goes from, if you start at 0, say, it's most typically written this way, of a times r to the k, which if you write it out will be a plus ar squared plus ar cubed plus dot dot dot. That's going to converge if the absolute value of r is less than 1. In fact, if and only if. IFF means if and only if the absolute value of r is less than 1, and it converges in that case to a over 1 minus r, and diverges otherwise. We can put this series in this form here that you see. Probably helpful to just write out the first few terms to help you see it. Some people can just look at this. It is a little tricky here, though, that this is starting at k equals 1, whereas this is starting at k equals 0. And you've got, instead of a kth power, you got a k plus 2 power and a k plus 1 power there. It's okay, just write it out. When k equals 1, so you're going to get 5 times, when k is 1, that'll be 2 cubed, and then 3 squared. When k is 2, you'll get a 2 to the 4th power and a 3 to the 3rd power. When k is 3, you'll get a 2 to the 5th power and a 3 to the 4th power, etc. There's your a, that's your first term, and it simplifies to 2 cubed is 8, times 5 is 40, divided by 9 is 49ths. And the r, it's called the common ratio. It's what I need to multiply each term by to get the next term. And pretty clearly that's 2/3. And yes, the absolute value of 2/3 is indeed less than 1, so the series is going to converge. It's going to converge to a over 1 minus r. 49ths over 1 minus 2/3 is 49ths over 1/3, which is 49ths times 3, which simplifies to 40/3, which would be 13 and 1/3, 13.3 repeating. Okay, that would be the numerical value of that sum. On to page number 3. Use the ratio test is the first problem. Use the ratio test in its weaker form we're going to get away with. I could give a harder problem where you have to use the stronger form. Use the ratio test to decide whether this series converges or not. Show your work and clearly state your answer. Also say if the ratio test leads to no conclusion, as it sometimes does. What's an example where the ratio test leads to no conclusion? Actually, the harmonic series is one example. Another series is, well, any series of the form 1 over k to the p, where p is positive. The ratio test will lead to no conclusion. Turns out this kind of series converges when p is bigger than 1 and diverges when p is less than or equal to 1. Something called the integral test is something you can use to verify that, but I'm not doing the integral test on this exam. We can hope that we can just think about an ordinary limit and not a limsup or a liminf. Absolute value of an plus 1 over an. These are positive terms here, so those absolute value signs can go away. A sub n plus 1 is going to be the exact same thing you're adding there, except replace n with n plus 1 in both spots. Dividing by a sub n will mean multiplying by the reciprocal of this. And then simplify. That 2 to the n cancels with 2 to the n plus 1, leaving a 2. The n factorial completely cancels with the n plus 1 factorial, leaving an n plus 1. So you've got the limit as n goes to infinity of 2 over n plus 1, which is most definitely 0, which is most definitely less than 1. Therefore, the series converges. By the ratio test. Number 16. Hope it's pretty clear this is a fundamental theorem of calculus problem. Variable in the upper limit of the integration, but it is an x to the fifth instead of an x. Maybe you've seen these kind of problems in calculus classes before. Show work to find the first positive critical point of capital F. So we are talking derivatives here. And also find f double prime as well. We need the fundamental theorem of calculus. We also need the chain rule. I can think of this function here as, let's call it, say, capital G of h of x, a composition of two functions, where capital G of x is the integral with just an x up top instead of x to the fifth, where the FTC applies directly, and h of x is the x to the fifth. That's the inside function for the chain rule, for the function composition. The chain rule would say capital F prime equals g prime of h of x times the derivative of the inside function h prime of x. Find g prime with the fundamental theorem of calculus. It's going to be sine of x cubed, except we need to plug h into g prime. So instead of x cubed, I have x to the fifth cubed, times the derivative of h, which is 5x to the fourth. So this is 5x to the fourth times sine of x to the 15th. There is the first derivative of this function. Therefore, the first positive critical point is where the first derivative is 0, the first positive value of x where it's 0. If I set this equal to 0 and solve for the first positive value of x where this is equal to 0, I can ignore that because that's only going to be 0 when x is 0. I only need to focus on that one. Sine, the first positive input for the sine function, that is 0, is when the input is pi. So x to the 15th would have to be pi, and therefore x, the first positive critical point, is going to be the 15th root of pi. Pi to the 1/15th power, which will be a number slightly bigger than 1. And it is positive, the first positive critical point. F double prime of x, okay, that's just a little bit of practice with the product rule and chain rule. Derivative of the first function, 5x to the fourth, is 20x cubed times the second function, plus the first function times the derivative of the second. Derivative of sine is cosine. Use the chain rule, multiply times the derivative of x to the 15th, which will be 15x to the 14th. That's the answer. We can simplify a little bit if we liked. 15 times 5 is going to be what? 75. X to the 4th times x to the 14th is x to the 18th. Cosine of x to the 15th. You know, you also could factor out a 5 out of both terms and an x cubed out of both terms, but it's not a big deal in a real analysis course. 17, more calculations. Let f of x equal 1 over 1 plus 2x. Do some algebraic manipulations, no calculus, to help you find the Taylor series for f centered at 1. Include the simplified form of the first 3 non-negative terms and also include the plus ... for full credit. And part B, what is the radius and interval of convergence for the series? So for my students, I'm expecting they know some things here, and they also know how to do some tricks in this kind of context. One thing to know is the exact same formula I showed you on the previous page. The formula for the sum of a geometric series, that's how we're going to get the answer without calculus. We don't have to take derivatives of this function and use the definition of the Taylor series. You want to get the terms to involve powers of x minus 1. It's centered at c equals 1. So we want to do some manipulations here to rewrite this function in a way that's going to, again, allow us to use this formula with r involving x minus 1. R won't equal x minus 1, but it will involve x minus 1. So how do you do that? Well, it's a trick. replace x with x minus 1. Wait, how can we do that? Well, if you compensate. By replacing x with x minus 1, I really subtracted 2 from the bottom of the fraction. 2 times negative 1. So to compensate, I need to add 2. Let me write this now. Why did I do that? Why did I put 2 minus signs? Because it's a plus. It's because I'm thinking about the minus sign here. I also need a 1 there instead of a 3. So I'm going to factor out a 3 out of the bottom, which can go up top as a 1/3. And doing so gives me this. That is the exact same function. Okay, just written in a weird form, but it's a form that's very nice because it's now in the form a over 1 minus r. A is 1/3, r is that thing. So, by the formula for the sum of a geometric series, it equals a, which is 1/3, plus a times r. R is the negative 2/3 x minus 1, plus a times r squared, plus a times r cubed, etc. I don't have to go further, though. This is going to be my first 3 non-zero terms. Now just simplify. 1/3 minus 2/9 times x minus 1 plus negative 2/3 squared is 4/9 times 1/3 is 4/27 x minus 1 squared, etc. And hopefully I didn't make a mistake. Yeah, I think this is good. What's the radius and interval of convergence? This will converge. I'll answer them both effectively at the same time. Since this is the r, this converges when the absolute value of r, which is negative 2/3 times x minus 1, is less than 1. Converges exactly when. I'll say if and only if. This inequality defines the interval of convergence, but we can simplify it. We can factor out a positive 2/3 out of the absolute value signs. That is okay to do. We can also multiply both sides by 3/2 to say the absolute value of x minus 1 must be less than 3/2, which is 1.5. And that defines the interval of convergence. In interval notation, the interval of convergence I, you're after all values of x whose distance to 1 is less than 1.5. It's the open interval from negative 1/2 to positive 5/2. Negative 0.5 to positive 2.5. Yeah. There's your interval of convergence, and it does not converge at the endpoints. You got to be careful because sometimes Taylor series do converge at endpoints, and you got to use some other knowledge to verify that. But in this case, it doesn't with geometric series like this. That's the interval of convergence. What's the radius? Draw a picture to help you see the radius. Well, it's the 1.5 if you want to just say that's the answer. Yeah, we converge between negative 0.5 and positive 2.5, not including the endpoints. The radius, thinking of 1 as the midpoint or center of the interval, is 1.5. That's 1.5 on both sides. That's the radius of convergence. If we were thinking of x as being a complex number instead of a real number, the interval of convergence becomes a disk of convergence in the complex plane, but the radius of convergence stays the same, and it really is a radius of a circle in that case. Next page. Another geometric series. Fun, fun, fun. This time I gave my students some help so they don't make a mistake, so I can test something different. There's a series. It is a geometric series. First term is 2/5. That's the A. Common ratio R is 3/4 x. That's what I say here. geometric. A is 2/5, R is 3/4 x, so that it converges when the absolute value of x is less than 4/3. It converges between negative 4/3 and positive 4/3, not including the endpoints. Also, it converges to this function of x, a over 1 minus r, which can be simplified to this. If you multiply the top and the bottom by, what would it be, 20, looks like, yeah, to get this simplified form. And so this is the Taylor series for this function centered at 0. It's centered at 0 because each of these has just a power of x instead of x minus something. Part A, use the ratio test once again to confirm the radius of convergence to be 4/3. Part B, use the given series to find the Taylor series of this weird function. Maybe you want to pause the video and think about how these functions are related. They are related to each other, and that's why we have kind of a weird function there. All right, ratio test. How are we going to do that? There's two ways to do this. There's sort of like a ratio test formula for the radius of convergence, where you effectively take the reciprocal of the coefficients of x, the powers of x here. I'm not going to do it that way. I'm going to think of this as being my a sub k, and think about the limit as k goes to infinity, or n goes to infinity, say. I could use a k, but it's not a big deal. Of the absolute value of a sub n plus 1 over a sub n. And here you really do need the absolute value signs because x could be positive or negative, and a sub k or a sub n depends on x. So a sub n plus 1, or a sub k plus 1, is what I get when I replace k here with n plus 1. Go ahead and keep the absolute value signs to start with. We'll get a 2/5 times 3/4 x to the k plus 1, or n plus 1, excuse me. And then divide by a sub n. It's the same thing, except you can take the reciprocal of everything. Or we can write a division symbol and have the thing itself in the bottom. 2/5 times, in parentheses, 3/4 x to the n. Lots of stuff cancels. The 2/5 cancel. 3/4 x to the n can't completely cancels, and you're left with partial cancellation there. You're left with a 3/4 x to the first. You can factor out the 3/4 and write it like this. And as far as confirming the radius of convergence is less than 1, it is good enough, it turns out, to consider the result of the ratio test in the context when we have convergence, when this limit is less than 1. This is going to be true if and only if the absolute value of x is less than 4/3. And that's enough to confirm that the radius of convergence is 4/3. Okay, so I'm not explaining it here. And I guess I wouldn't expect that of my students. But that effectively confirms that as the radius of convergence. Now careful, this calculation doesn't confirm or disprove whether the series converges or diverges at the endpoints. It won't, because it is geometric, but the ratio test calculation is not enough to prove or disprove it. And in fact, for part B, we are going to actually get a series that does converge at one of the endpoints, though I don't ask for the interval of convergence here. And what's the relationship? How do you do part B? I hope you did think about it and realize that g prime of x does equal f of x. G is an antiderivative of f. Therefore, to find the Taylor series for g centered at 0, I just need to integrate the series for f centered at 0, term by term. And that is okay to do, it turns out, as long as we are inside the interval of convergence. G of x is the integral of f of x. I could write it as a definite integral, but I'm not going to bother for sake of simplicity. As an indefinite integral, I will put a plus c in there actually at the beginning. C plus, now integrate term by term. Integrate 2/5, get 2/5 x. Integrate 3/10 x, get 3/20 x squared. Integrate 9/40 x squared, get what? 3/40 x cubed. Integrate 27 over 160, get 27 x cubed, get 27 over 160 times 4 will be 640 x to the fourth, etc. However, this is a particular function. C is not just anything. I need this fact to figure out what C is. Negative 8/15 ln of 20 is, in fact, g of 0. Plug in x equals 0 there. And that's c plus all the other terms when you plug in x equals 0. In fact, that must equal c. This thing here must equal c. Therefore, g of x, its Taylor series, centered at 0, will be this same series with c equal to that, and it, in fact, will equal g, it turns out. I'm writing equality even though I haven't talked about why they're equal. That'll be the Taylor series for g of x centered at 0. It will certainly converge when x is strictly between negative 4/3 and positive 4/3. It possibly could also converge at one or two more points, at the endpoints, either at x equals positive 4/3 or x equals negative 4/3 or both. And my guess, if I had to guess what happens here, though I'm not going to take the time to confirm it, is that it will converge at x equals negative 4/3, but probably not positive 4/3. That's my guess. You can try to take the time to confirm it. When x is negative 4/3, it'll end up converging by the alternating series test. When x is positive 4/3, I'm guessing we probably get something related to the harmonic series and it'll diverge, I'm guessing. And even at negative 4/3, even though it'll converge non-absolutely, if my guesses are right. 19. Series of powers of cosine squared. Part A, using facts you know about geometric series again. Wow, geometric series are pretty important. They are. So I'm really emphasizing them here. And trigonometry, explain why the series converges pointwise to cotangent squared on the interval from 0 to pi, the open interval. First thing to realize is this is a geometric series for any fixed value of x. It's a geometric series. The first term, a, is cos squared x. And in fact, the common ratio is also cos squared x. It is a geometric series for any fixed value of x. And as long as cos squared x is less than 1 in absolute value, it's going to converge. And if x is between 0 and pi, strictly between 0 and pi, that will be true. Cosine of 0 is 1, and therefore cos squared of 0 is 1. But if x is slightly bigger than 0, then this is less than 1. Cosine of pi is 1, and cos squared of pi is 1. But if x is strictly between 0 and pi, this is an open interval, this is going to be true. This is true if x is in the open interval from 0 to pi. Therefore, I can use the formula for the geometric series to say this converges to a over 1 minus r, cos squared x over 1 minus sine squared, over 1 minus cos squared x, sorry, jumping ahead of myself. But then by a trig identity, the bottom becomes sine squared x. And that is cotangent squared x by definition of cotangent as cosine over sine. Part B, with the help of the Weierstrass M-Test, prove that the series converges uniformly to cotangent squared on the closed interval from pi over 3 to pi over 2. Different interval, you might scratch your head and wonder why there. It's it is a good thing to make a smaller interval. It's not the only interval that I could have picked, but it is an interval that's convenient to pick. Need to recall what the Weierstrass M-Test said. Suppose fk is a sequence of functions defined in an interval I. Our interval here is from the closed interval from pi over 3 to pi over 2. Also suppose that, I really should have said back here, for each k, there exists an mk such that this is true. An upper bound on the fk's for all x in the interval. Then if that series converges, then this series of functions converges uniformly on the interval. So the fk's here, fk of x, go ahead and put the input x, is cos of x to the 2k power. Okay, so I'm not going to write sentences here. I tell my students to write sentences. I could say, let this be true for each k and for all x in the interval. These functions, cos squared, cos to the 4th, cos to the 6th, are always positive on this interval, and in fact they are decreasing. The cosine function, on this interval, not this entire interval, but this one there, the cosine function from 0 to pi over 2 has a graph that looks like this. So that's y equals cos x as x goes from 0 to pi over 2. So it's decreasing. It's also decreasing from pi over 3 to pi over 2. And that's going to imply all these functions are also decreasing from pi over 3 to pi over 2. In other words, they are maximized when x is pi over 3. And in fact, cosine of pi over 3 is something you should memorize to be 1/2. Second coordinate of that point is 1/2. This is 1 up there. So what you can do is you can let mk be the maximum value of cosine of x to the 2k power on this interval, which is going to be 1/2 to the k power to the 2k power, or if you prefer, 1 over 2 to the 2k power. Then we are using properties of cosine here that we know. The absolute value of fk of x, the absolute value of cos of x to the 2k power, which is going to be positive on the interval. So I can get rid of the absolute value signs, though you don't have to, is less than or equal to mk for each k and for all x in the interval from pi over 3 to pi over 2. That's just knowledge of the cosine function's behavior. Pre-calc knowledge. And the mk's, if you put them in a series, form, yet again, a geometric series. One half to the 2k power is k starting at 1. It's k, 1 times 2 is 2. 1/2 squared is 1/4. Then we get 1/2 to the 4th power is 1/16. Then 1/2 to the 6th power is 1 over 64, etc. Converges. It's geometric with r equal to 1/4, which has an absolute value less than 1. I won't write that out. I will write that what this converges to, 1/4 over 1 minus 1/4, 1/4 over 3/4, which is 1/3. Therefore, the Weierstrass M-Test implies that the original series converges uniformly on the given interval to the given function that it converges pointwise to. Converges uniformly on the interval that we're talking about here, pi over 3 to pi over 2, to the function it converges pointwise to, which is cotangent square root of x. All right, take a breath. 2 more pages. They're proofs, and the very last one's a difficult proof. Save time, I'm just going to talk about the ideas of the proofs. I don't want this video to be too terribly long. It's the last problem. It's a Riemann integrability proof that is the hardest. Though these things are not pieces of cake either, unless you know the tricks of the trade, you know how to use theorems in good ways. They are important facts that we're considering here. This one ultimately is considering something called the intermediate value theorem. Effectively, we're ultimately saying can be proved with the fundamental theorem of calculus, though we can also prove it without the fundamental theorem of calculus. It's just an illustration of the use of the fundamental theorem of calculus. Part A, okay, well, little f's continuous and always positive. Part A, give a geometric interpretation of the average value over the interval. That's a calculus problem. You can draw a picture. Let's go ahead and do that right away. Let's say the interval looks like this. I'm not going to write out my geometric interpretation, but I will draw a picture and describe it for you. There's our function. Its graph, y equals f of x. It's continuous, being positive. The integral is going to give you the area under the curve. This formula, which is the definition of average value, is equivalent to this equation, the integral from a to b of f equaling v times b minus a. And b minus a is the length of the interval here. This can be interpreted as the area of a rectangle. So what we're saying is the area under the curve equals the area of some rectangle whose base is from a to b. There's some height of the rectangle, v, that will make the area under the curve equal to the area of some rectangle, and intuitively that rectangle would have to go through the graph maybe about like this. And the area when it's above the graph would cancel out the area when it's below the graph, so you'd have the same area, v times b minus a, and these are going to be equal. So that's an interpretation of our average value. Part B. Use the fundamental theorem of calculus and the ordinary mean value theorem for derivatives to prove, okay, it's not quite the intermediate value theorem. There's a number c in the interval where f of c equals v, the average value. Okay. So it's more like it turns out to be more like a mean value theorem. It turns out to be more like a mean value theorem for integrals, but I'm not going to get into details. Gave a hint. Start your proof by defining a function capital F with this formula. We've seen that before. Capital F is going to be an antiderivative of little f. So we go ahead and say, let capital F of x be that integral. Got to use what I'm being told to use. It'd be hard to know what to do, I think, unless you have enough experience without being told what to do here. So I'm going to use the fundamental theorem of calculus. This is set up to do so. Since little f is continuous everywhere on the interval, capital F prime of x equals little f of x for all x in the interval, which is from a to b, closed interval from a to b. Derivative. The ordinary mean value theorem for derivatives is related to derivatives of differentiable functions. It stated that if you've got a function that's continuous on a closed interval and differentiable on the open interval, then something's true. Our capital F here is actually differentiable on the entire closed interval, which also means it's continuous on the entire closed interval. Yeah, because I'm talking about the derivative of capital F, I'm going to apply the mean value theorem to capital F. Mean value theorem applied to capital F on this interval means there exists a number c, turns out in the open interval, though the open interval is a subset of the closed interval, such that, here's the conclusion, capital F prime of c equals capital F of b minus capital F of a divided by b minus a. And if you graph capital F, what you're saying is the there's some value of c where the slope of the tangent line is equal to the slope of the secant line, if I graph capital F, which I'm not doing. But capital F has this formula, and in this derivative, I can rewrite this equation using those facts, i.e. capital F prime of c is little f of c. Capital F of b, use this formula, is the integral from a to b of little f. Capital F of a, by this formula, is the integral from a to a of little f, divided by b minus a. That's 0. And this fraction can be rewritten as 1 over b minus a times the integral from a to b of f, which, by definition, is the average value. That's v. Done. Okay? So, yeah, this would be tricky to do without some hints. It's not too bad once you have the hints and once you realize, okay, I've got to use the hints in some way. There we go. Yeah, I said it wrong. It's not really the intermediate value theorem. It's really related to the mean value theorem for integrals. I can multiply both sides by b minus a as well. So I can say there's some c in the interval where the integral of f from a to b equals f of c times b minus a. F attains its average value. 21. Two more problems. Suppose f and g are defined on R. I'm saying on the entire real line to make things a little simpler. You actually can prove what we need to prove here on certain closed intervals. You can make those kinds of assumptions here, but I'm just trying to make it simple. I'm also saying let's just assume it's got infinitely many different derivatives that are all continuous. So therefore all functions are Riemann integrable, and we can apply the fundamental theorem of calculus. Most definitely can be used. Okay, so don't want to worry about technicalities with assumptions. That's the point here. Use the FTC and a derivative rule, and give the name of the derivative rule, to prove that this equation is true. Kind of a weird looking equation. Maybe you've never seen it before. It's very much related to something you learned in calculus. It's very much related to substitution, U substitution in calculus, or in our textbook that we use, W substitution. I'll explain how after I do the proof. This seems difficult, doesn't it? Use the FTC. We got to use the FTC. When I teach this, I actually work through this problem with my students, and so the idea is, okay, they've seen this proof before. And I think I do it in a more specialized case with closed intervals. It'd be pretty hard to know what to do from scratch. How in the world am I going to use the FTC? Well, okay, so try to get some intuition here. Think about the integral on the right, which is simpler looking, at least for the integrand. If I was going to do an integral like that, it would be nice to have an antiderivative of little f to do the integral. Maybe I should go ahead and define an antiderivative of little f. The FTC allows me to do that when little f is continuous, which I'm assuming. Let capital F of x equal the integral of little f. What should the limits of integration be? Well, the upper limit should be x for sure. What's the lower limit? G of a? Turns out it doesn't matter. I want capital F to be any old antiderivative of little f. And that's where, again, assuming everything is defined on the entire real line makes things a little simpler that way. I could even pick 0, but I could pick 1, I could pick 2, I could pick negative 17, I could pick a, I could pick g of a. It doesn't matter. Anything I pick for that lower limit, as long as that upper limit is x, is going to give me an antiderivative of little f. The FTC implies capital F prime of x equals little f of x for all x in the real line. And therefore, the FTC also implies that the integral on the right of little f from g of a to g of b, g of a and g of b are just numbers, a and b are fixed, g is a function, is capital F of the upper limit, g of b, minus capital F of the lower limit, g of a. Okay. Haven't used the derivative rule yet. Evidently, the left-hand side, the integral on the left, must equal this. Are you getting a feel for this at all? This integral's got to equal this if this is going to be true. And it's still a difference of functions. This one, f of g evaluated at b and f of g evaluated at a, the exact limits of integration here. That's where light bulbs should be going off. Let, say, I don't know, capital H of x equal capital F of g of x. This is going to be an antiderivative of that. Why? The chain rule. Chain rule, that's the derivative rule we need. We've got a composition there. It says h prime of x equals capital F prime of g of x times g prime of x. Capital F prime is little f. And using this kind of notation with the circle in there for function composition, this is f circle g of x times g prime of x. And if you really wanted to go hog wild with this, you could say that's, like you see there, f circle g times g prime of x. Kind of weird, but you could do that. It's implying this is a multiplication. F circle g, function composition, f of g times g prime of x. By definition would be this function, which by definition would be this function. So these are just alternative notations for each other. So once again, using the FTC, so what we've verified here is that capital H prime is an antiderivative of f circle g times g prime. So the FTC, once again, comes to the rescue to say the integral of f circle g, f composed g, times g prime will be h of b minus h of a. But what is h of x? It's capital F of g of x. This is capital F of g of b minus capital F of g of a. And lo and behold, we have a match. Match. Happy. Okay? And that essentially is the proof. This is related to substitution, like I said. Consider a simple substitution problem. Oh, I don't know. How about the integral from 1 to 3 of 2x e to the x squared? You should recall from calculus that if you do a substitution, u equals x squared, du equals 2x dx. This is going to be the integral of e to the u du. But you do need to change the limits of integration. That's the point of the problem, in fact. When x is 1, u is 1 squared is also 1. When x is 3, u is 3 squared is 9. We're saying these two integrals are equal. That's fitting this pattern here. The f, this is f of u right there. That's the integral on the right. F of u is e to the u. You could say f of x is e to the x. What's g? The left integrand is f composed g times g prime. F is e to the u. This is e to the x squared here. G has got to be the x squared. That's g of x. And this is g prime of x. And the substitution here, u equals x squared, is g of x. And this lower limit is, I should have picked something other than 1. This lower limit is g of 1. This upper limit is g of 3. That's the relationship. On to the final problem. Save the best for last. Need an entire page for this one. Here's the definition of Riemann integrability to prove that the following function is Riemann integrable over the interval, the closed interval from 2 to 8. This is a piecewise function. Okay, it's really impossible to do these things without some scratch work. First bit of scratch work to do is to go ahead and graph this function to guess what the integral would be. Because if you don't know what the value of the integral is going to be, it'd be very difficult to use the definition of Riemann integrability to prove that it's Riemann integrable. So what's the graph of this function look like? Let's graph it over here. As x goes from 2 to 4, the value of the function is 3, including the endpoints. When as x goes from 4 to 8, the value of the function is 5, not including that left endpoint. Now, including the right endpoint there, but not the left endpoint there, is an arbitrary choice. I could have made this an open circle and not a closed circle. I could have made that a strict inequality and this a less than or equal to. Doesn't matter, it turns out. Doesn't affect the area under the curve. And what is the area under the curve? That area is going to be base times height is 2 times 3 is 6. And this area, these are rectangles, is going to be base times height is 4 times 5 is 20. So the total is 26. We think the integral is equal to 26. Look at this and you say, how could this be difficult? The integral's got to be 26. That's the area under the curve. Well, okay, but the definition of Riemann integrability is a difficult thing to deal with. Why? Do math professors just want to make things difficult? They only make things difficult when they have to, okay? And when you're doing the theory, when you're trying to prove abstract facts like every continuous function is Riemann integrable over closed and bounded intervals, you need general definitions to rigorously prove things, and that makes it difficult. And it's just, you can't avoid it, really. Now, with Riemann integrability, there's really two approaches. One deals with what are called upper and lower integrals, and deals with sups and infs. Rudin's book does it that way, for example. But the book I use, which by the way is this book by Russell Gordon, is a simpler book, and it does it in, I think, a simpler way, though it's simpler conceptually, I think, but it doesn't make the proofs easier. They talk about arbitrary Riemann sums, where you're thinking about approximating rectangles, and you're thinking about finding heights of those rectangles by plugging in sort of arbitrary points in your subintervals. Tag partitions are the terminology and the notation for doing that. Okay, maybe you don't know quite what I'm talking about here. Let's get into the details of some scratch work here. I want to, no matter what epsilon is, no matter how small, be able to choose partitions of the interval, in this case from 2 to 8, so that the subintervals that I get, which are the bases of the rectangles, are all sufficiently small enough to make the areas of all the rectangles within epsilon of 26, the area under the curve that I can see there. In Russell Gordon's book, this notation, S of f comma tp, well, it's a little weird. T is a pre-superscript. Doesn't want to make it a post-superscript because it would make it, you think it's a power. Is notation, shorthand notation for a Riemann sum that looks like this, where the index of summation, say call it k, goes from 1 to some number n. I plug in a number called tk into f. That's going to be the height of my approximating rectangles, times the base, which in calculus classes is often just called delta x or delta t. And it's always the same. Each rectangle has the same width. But we want to allow, in the more general theory, for arbitrary widths. So we would write, say, x sub k minus x sub k minus 1. I want the distance between that quantity, let's put the want down here, and 26 to be less than epsilon. Okay? So I could replace that symbol with the summation as well. It's good to think about what this is equivalent to. This is equivalent to saying I want the Riemann sum itself to be between 26 minus epsilon and 26 plus epsilon by taking what's called the norm of the tag partition to be sufficiently small, which effectively means all your rectangles are sufficiently skinny, which means these numbers are all sufficiently small. Now, in a problem like this, where you've got a piecewise function with two pieces, simpler than 3 pieces or 4 pieces or 5 pieces, you want to think about your Riemann sum here as being made up of 2 pieces. One where the tags, these are called tags, are in the first interval, and one where they're in the second. Why? Because the function has 2 different outputs for such tags. And it's good that it's a constant function in each interval. It would be harder if it wasn't. So we could think of this as being a summation. K goes from 1 to, say, m of f of t sub k. Let me go ahead and just shorthand notation this and call it delta x sub k. It's not a constant. Delta x sub k, when these tags are in the closed interval from 2 to 4, and the other sum, k goes from m plus 1 to n of f of t sub k times delta x sub k, where these tags are in the interval from 4 to 8, not including the endpoint 4. You would be able to write any Riemann sum in this situation in this form as long as you had enough intervals so that there were enough tags that, m is at least 1, say, and n is at least 2, and you've got the t's in these intervals. You'd be able to write it in that form. And in the abstract, we can just sort of assume, I think, n is big enough and the intervals, the delta x's are small enough that we can do this and not worry about the details too much. I mean, you could get real technical about it, but that's not really worry about it. That's not really the point. Because these function values are constant, these values are all 3s, and these values are all 5s. Those are the constant outputs, 3 and 5. And so what I really have here is 3 times the sum of these delta xk's, and here I have 5 times the sum of these delta xk's. I can factor the 3 and the 5 out in front of the summations. And the sum of the corresponding delta xk's, well, for the first one, is going to be, well, close to 4 minus 2, close to 2. And for the second one, it will be close to 8 minus 4, close to 4. Equal to 2 and 4? Not necessarily, but close. If I choose the norm of the partition to be sufficiently small. What is the norm of the partition? Notationally, it's written like this. It's the maximum of the differences of the xk's. It's the maximum width of a rectangle. If you can make the norm of the partition, the tag partition, sufficiently small, then all these differences and all these delta xk's will be sufficiently small to hopefully make this really close to 3 times 2 and this really close to 5 times 4, and therefore the entire sum of those close to 26 in the end. Okay? But how do you choose the delta as the measure of smallness of this norm? This is probably still the trickiest part here. You want to choose, to ultimately get to this involving epsilon. Let's see. I was thinking about this ahead of time, and now I'm feeling a little confused. Think about this here. Oops, this is an M. You want this to be between 3 times 2 minus something. I'll call this something delta. And let me put the 3 in there, sorry. 3 times 2 plus delta. In other words, 6 minus delta and 6 plus delta. Delta is unspecified. This is part of the scratch work. And the other one, 5 times the other summation, k goes from m plus 1 to n, to be between 5 times 4 minus delta and 5 times 4 minus delta and 5 times 4 plus delta. In other words, 20 minus delta and 20 plus delta. Because if you can choose delta to make that happen, that's going to mean the sum of these two things, which is the Riemann sum in the middle, will be between, let's see. Oh, and I made a mistake here, I think, in my thinking. I think I need the 3 here and here, and 3 here and here, and the 5 here and here as well. Intuitively, this is not easy. Intuitively, when I add these things up, yeah, this gives me close to the length of this interval, except with a cushion of delta on either side, possibly. I'm not explaining this well. Sorry about that, and I'm running low on time. I think I better just go for it here. This is a 6 minus 3 delta, 6 plus 3 delta, a 20 minus 5 delta, and a 20 plus 5 delta. If I add all these inequalities, I get 26 minus 8 delta and 26 plus 8 delta. And so effectively, to relate it to this, I want to choose delta so that 8 delta equals epsilon, or if you prefer, 8 delta is less than epsilon. Choose delta to be less than epsilon over 8. I didn't explain it so well right there. I think for the sake of time, I better not spend a ton of time. And then with a proof, I'd try to write some sentences here. So how do you start a proof? You start it the same way often you start limit proofs. Let epsilon greater than 0 be given. Choose delta positive so that it's less than epsilon over 8. Or I really could choose delta to equal epsilon over 8. Or let delta equal epsilon over 8. Either way is okay. You want to assume you've got a tag partition. TP, which in Russell Gordon's book is written like this, as a list of intervals, effectively, where a list of actually ordered pairs where the first element are the tags and the second element, so the interval is kind of strange. Let this be a tagged partition of the interval from 2 to 8 with norm maximum of the delta xk's less than delta, which, okay, I'm going to go ahead and just do that, equal to epsilon over 8. And it's less than it. Now think about the Riemann sums. Not worrying about technicalities, whether we really can split it up like this, which might be fishy, like if n is 1, for example. Assume n is large enough that we can split it up like that, and this is small enough. Then the Riemann sum corresponding to that tag partition, which we can initially write like this, k here, where delta x sub k I'm assuming is xk minus 1. I could write some words to say it can be written in this form. There's some m where it can be written like this, and where these TKs, k goes from 1 to m, are all in the interval from 2 to 4, and the other TKs where k goes from m plus 1 to n are all in the interval from 4 to 8. I mean, that could be said in words, and you definitely can do that. And therefore equals, this is 3 and can be factored out, 3 times this summation plus 5 times the other summation. Okay, and so here's the trickiest part, the part where I get sort of stuck in my explanation. This summation, sum of the first delta m delta xk's, length of the first m intervals, because I chose these tags to be in 2 to 4, the right, okay, here's a better explanation. The rightmost of these tags, t sub m, the biggest possible value it could be is 4. And that 4 could theoretically be the left endpoint of the mth interval. I could draw a picture to help. And so this summation is definitely going to be less than 2 plus delta. And you could also say it's greater than 2 minus delta. This is between 2 minus delta and 2 plus delta, which is between 2 minus epsilon over 8 and 2 plus epsilon over 8, because delta equals epsilon over 8. Okay, this is a little bit better. Okay, I think we got it here. And this summation is going to be between 4 plus delta over 8, 4 minus delta epsilon over 8, and 4 plus epsilon over 8. And again, to rigorously prove that, really should add more explanation. You could say, you know, well, for the m plus first interval, the t sub m plus 1 could, in theory, be the left endpoint of the interval from 4 to 8. It could be 4, in fact. And that could be the right endpoint of that m plus first interval. So when you add up all the lengths of these intervals down here, it could be a little longer than the interval from 4 to 8. There could be overlap into the first interval. A little confusing, but that is a little bit more precise description of what's going on. And so in the end now, what you can say is, therefore, our Riemann sum here is between 3 times 2 minus epsilon over 8 plus 5 times 4 minus epsilon over 8 and 3 times 2 plus epsilon over 8 plus 5 times 4 plus epsilon over 8. Now simplify. What does this simplify to? 6 minus 3 epsilon over 8 plus 20 minus 5 epsilon over 8, which simplifies to 26 minus 8 epsilon over 8, which is epsilon. And this simplifies to 6 plus 3 epsilon over 8 plus 20 plus 5 epsilon over 8, which simplifies to 26 plus 8 epsilon over 8, which is epsilon. And we're effectively done. Now I could subtract epsilon from, well, I could rewrite these inequalities in this form. Okay? That means we're done. That's hard, okay? And I know my explanation wasn't best, but I hope you got the basic idea anyway. Thanks for watching.